Welcome to this explainer. Today, we're decoding the invisible enemy of engineering. It's a phenomenon that has literally brought down airplanes, collapsed massive bridges, and shattered heavy machinery, often without a single warning sign. We're talking about fatigue failure. If you've ever found yourself wondering how solid, incredibly strong metal structures can just spontaneously snap in half, well, you're definitely in the right place. So think about it. Why do parts that are subjected to loads well below their maximum yield strength suddenly just give out? It kind of defies logic at first glance, right? Well, consider a highly relatable human analogy. Just like repeating a really simple physical task over and over again eventually exhausts us, metallic components get fatigued too. When a material undergoes repetitive, variable loading over a long period of time, it physically tires out until it literally breaks. It's not about how heavy the load is, it's about how many times that load is applied. Here's our roadmap for the explainer today. 1. The mystery of fatigue. 2. 3 stages of failure. 3. SN diagrams and cycles. 4. The endurance limit threshold. And 5. Goodman and Soderberg criteria. Basically, we're going to start by diagnosing the physical reality of how these cracks form, then transition to the graphical data engineers use to track them, and finally, we'll dive into the math that prevents these catastrophic failures before they ever happen.
Okay, Section 1, the mystery of fatigue. Let's just dive right in and establish exactly what we're dealing with here.
The American Society for Testing and Materials has a very specific definition. They say fatigue is the process of progressive, localized, permanent structural changes occurring in a material subjected to fluctuating stresses, culminating in cracks or a complete fracture. Now, what makes this so incredibly dangerous is that, unlike static failures, where a part visibly bends or deforms, giving you a clear warning like, hey, replace me, fatigue happens invisibly. It happens deep inside the material over a huge number of cycles, making it the ultimate silent structural killer. Moving on to Section 2, 3 stages of failure. Let's look at the exact physical mechanism of how this invisible killer actually does its damage. It happens in 3 terrifyingly quiet stages. First up, crack initiation. A microscopic crack usually starts at a tiny point of high-stress concentration. Think a notch, a keyway, or even just a scratch on the surface. Second is crack propagation. As the cycles continue, this tiny crack grows. And here's the worst part. As the crack grows, it shrinks the actual load-bearing area of the part. That causes the stress to spike even higher, which makes the crack grow even faster. Finally, we hit stage 3, final fracture. The remaining intact metal becomes just too small to hold the load, and boom, the component snaps suddenly without warning, leaving a break that looks surprisingly like a brittle material failure. Which brings us to Section 3, SN diagrams and cycles. Since we obviously can't see these cracks forming, engineers map out this failure using some highly structured data. Check out the SN diagram. This is essentially the cornerstone of all fatigue design. On the vertical axis, we have S for fatigue strength, and on the horizontal axis, N for the number of stress cycles. Notice how it's plotted on a log-log scale? That's because we aren't just talking about a few bends. We're dealing with thousands, millions, or even hundreds of millions of cycles. By plotting test data here, engineers can predict if a part is going to have a finite life, meaning it's definitely going to fail, or an infinite life. We generally split this life cycle into 2 distinct regions. Low cycle fatigue happens in under 1,000 cycles. This involves actual plastic strain and deformation. Think of highly stressed, short-lived devices, like a single-use missile. High cycle fatigue, on the other hand, deals with cycles way beyond that 1,000 mark. This is where most mechanical moving parts operate, and where the SN curve really helps us define the boundaries between a finite and an infinite lifespan. Right, Section 4, the endurance limit threshold. This introduces a truly fascinating phenomenon in materials science. And this brilliantly illustrates that magic property. If you look at the curve for ferrous metals like steel, you'll spot a distinct knee in the graph. At a certain point, usually around 1,000,000 cycles, the curve just flattens out entirely into a horizontal line. The stress level at that flat line is called the endurance limit. So the absolute game changer here is if you can design your component so the cyclic stress stays below that exact horizontal line, the steel will theoretically never fail from fatigue, literally infinite life. But hold on, because that rule is definitely not universal. Look at the stark contrast with non-ferrous materials, like aluminum or copper alloys. Their curves never truly go horizontal. The strength just continuously declines as the cycles add up. This means that for non-ferrous metals, there's no true infinite life threshold. Eventually, if you subject them to enough cycles, they will inevitably fail. No way around it.
Finally, Section 5, Goodman and Soderberg criteria. Knowing all this behavior, how do we mathematically design our way out of a catastrophic failure?
First, we have to deal with the messy reality of fluctuating loads. A fully reversible load, where the stress perfectly swings from maximum tension to maximum compression, is the absolute worst-case scenario used in lab testing. But out in the real world, loads are almost always offset. So engineers have to calculate the mean stress, which is the average load applied, and the stress amplitude, which is how much it bounces around that average. We need a way to combine these to find a safe operating zone. And that leads us to our primary engineering criteria. We plot mean stress on the x-axis and stress amplitude on the y-axis. The modified Goodman line connects the endurance limit to the ultimate strength of the material. But look right below it. That's the Soderberg line. It connects the endurance limit to the material's yield strength instead. Because yield strength is lower than ultimate strength, the Soderberg line gives us a much tighter, way more conservative, and therefore much safer boundary to work inside of. So how do engineers actually build this into a design? Well, plotting the endurance limit on the y-axis and yield stress on the x-axis draws our absolute failure line. But nobody wants to design right up to the ragged edge of failure, right? So we apply a factor of safety. We'll call it N. By dividing our limits by this safety factor, we essentially shrink our boundary, drawing a new line safely closer to the origin. Thanks to a clever little trick using similar triangles, any point operating within this new boundary is mathematically guaranteed safe from both yielding and fatigue. And all that visual geometry distills down into one remarkably elegant formula, the Soderberg equation. You just take the stress amplitude, divide it by the endurance limit, and add that to the mean stress divided by the yield strength. Set the whole thing equal to 1 over your factor of safety. It is a brilliant, simple equation that lets an engineer take all those chaotic, fluctuating variables of real-world loads and definitively check if a part is going to survive or snap.
Which leaves us with a pretty profound realization. As you drive over a bridge, fly in an airplane, or even just ride an elevator today, countless metal components all around you are constantly flexing and relaxing. How many invisible, microscopic cracks are the Goodman and Soderberg criteria protecting you from at this very moment? The hidden mathematical rigor holding our modern world together is honestly something to marvel at. Thanks for joining me on this explainer, and keep looking a little deeper at the structures around you.